Yeah, thanks a lot, Ida. And yeah, it's a great pleasure to present some of these results here and that we've been working on for the last 3 years. Um, and it really is it's a huge problem with the plastic area. And I just want to get into how we can combine it also with CO2 capture. But of course, with the anthropogenic emissions, we have today about 37 gigatons per year. We really need to have access to millions of tons of sorbents. And if we look at some of the different types, of course, we have solid sorbents, and they really are advantageous compared to the conventional aqueous amines that are used, particularly because of the easier regeneration for carbon capture or liberation and CO2 liberation, but also the stability of these types of materials. And here's just some examples of some of them that you can see on the screen. But of course, the problem is that the production capacity of these materials are not very high, and the costs are also significantly high still. And so one of the questions that I have, or my team has, and also that of one of the other core PIs, Ji-Wang Lee and his team, are there opportunities also for other types of materials that we can that we actually have plenty of, and we really don't know what to do with the waste? And one of these areas is the plastics. And you can see we produce, over 400 million tons of plastics every year. And if you look at the right-hand figure and you look up on the top right, you can see that the only the amount of recycling that's occurring, and this is basically mechanical recycling, is under 9% of those 400 million tons that we're producing. So the question is, what can we do with these types of materials? And but just also to get an idea of the what does this number mean? These 400 million tons. If you make the human meatball of humanity, right? It's sort of disgusting after our lunch here, but it fits very nicely with Lasse's talk. So, but you would see that would be about the amount that we're producing of plastics every year. And this is every year, right? Of the weight of the human population. And if you go to the left side, you can see the plastic production is increasing, and we can actually basically predict by 2060 we'll have 3 times that, so almost 1.2 gigatons of plastics. And if we're not doing anything with that plastic recycling, then this is going to be a huge issue. So the question is, are there any opportunities of transforming these waste plastics into carbon capture materials, which we really need to, for the problems that have arisen. And these are just some examples of the waste streams that we have. If you look on the top left, I mean, in Europe, we throw away 35 million mattresses away every year. 35 million. Stack them up on top of each other. That's 7,000 kilometers. 7,000 kilometers of mattresses every year just from Europe. In China, it's 60 million. Even the wind turbine blades, we heard a little bit about wind turbines in the beginning, but the way we dispose of them is just basically landfilling because we cannot do anything with it. And another example are single-use gloves. We produce 180 million gloves per year, or a billion gloves, and also shoes. You can see the amount there. So there's some real opportunity because there's absolutely no recycling technologies for these types of materials. This is just total waste, right? And so one of the, and I should say all the credit to Simon and the team that's been working there, you'll see the rest, but Simon was the one who started on this, on some of these projects. And the idea is very simple. It's to take plastics, polymers that actually incorporate them nitrogen, and somehow transform them into something, that nitrogen into an amine that could capture the CO2. And I should say the process that we have here is basically the simplest that you can have, because we're actually, the only thing we're doing is a chemical reaction using the simplest molecule of the universe, which is hydrogen. That's all what we're adding to that polymer, and we can transform it into something that binds CO2 through a thermal swing sorption. So that's the idea, and some of the materials we're looking at are nitrile butadiene rubbers, which actually contain these nitrile groups. I'm sorry, there's some chemistry I have to go through. And also I'll just talk a little bit about the styrene butadiene styrenes, which is also something Simon and the team has been working on. And all of this, I mean, one of the things that we're working on is using catalysis. We have to promote the reaction. We use catalysis with transition metal catalysis, in this case, ruthenium. And this doesn't come from nowhere. In fact, we've been working on closed loop recycling of plastics for several years using transition metal catalysis. And so what we want to do is adapt that technology now to looking at how to modify these plastics for carbon capture. And here's some examples. And again, there's a lot of figures there, but just look at the left hand on the graph there. But we can see the acrylonitrile content in acrylonitrile butadiene rubber is about 40%. And these catalysts are capable of reducing a number of those, a percentage of those nitriles, and that's what those percentages are. So it corresponds to 74% of that acrylonitrile in the polymer it has been modified. And we screened a bunch of different catalysts and so on. And the way we check that is we can do some chemical means by looking at what is accessible, okay, for the chemical reactions. And so this is sort of the optimized, where we take a nitrile butadiene rubber that we can buy, we convert it then to the reduction through a ruthenium catalyst, and then we cryo mill it, and simply to get sort of uniform small particles. We do that to all the materials, so because sometimes you end up with these chunks and so on. So just to get them uniform so we have something to compare with. And again, some details. We can use some fancy techniques, one called C13 cross-polarization magic angle spinning, NMR spectroscopy. And from that, you can, I do know that, but we have some really good colleagues, Ms. Nielsen from our department, and you can actually find out how much of the material is reduced and so on. You can use also Fourier transform IR. But I think what was really cool is actually starting this, and we're using thermogravimetric analysis. And when Simon was looking at this, we had a suspicion these materials were not going to be very good because they're not porous, okay? So in other words, there's no cavities for the CO2 to go into. And surely enough, if you look at it, this is at 100% CO2, 25 degrees and 50 degrees, the capacities for CO2 capture is not that great. But what was really cool about this material is that its capacity was higher even at higher temperatures, actually increased considerably at 90 degrees. And 90 degrees is a typical flue gas temperature for certain power plants. So that was pretty cool. And that was unexpected because we would expect the reverse, that the capture should be better at lower temperatures because you need heating to release the CO2. And yet we were getting better values at higher CO2. This is an example of styrene butadiene rubber, which has no nitrile, so it has no nitrogen. But again, we can do some funky chemical reactions and introduce this nitrogen, which I won't go into too much detail, but just to say that it works. And we can even do it with a nitrile butadiene rubber. So Simon's done some really nice work with that, introducing more nitrogen because we have this butadiene in there. Anyways, and that's shown in the examples behind me. These are some of the examples that we've used. There's the chemical processes that we've made nitrile butadiene rubber, both with just adding hydrogen, but also adding hydrogen cyanide and then reducing to increase the nitrogen content. And then we've also taken other materials, so for example, from a shoe sole, and converted that into also carbon capture materials. And so just to show you some of the details, these were the first results where we're looking at measuring how much CO2 is binding to these materials over time, and over 5 hours in 100% CO2. And again, some of the material, if you're looking at the left, look at the left, some of these materials were doing pretty good. The best was at 90 degrees again, if you look at the one all the way to the left, with a capacity of 3 millimoles per gram, which is about a 14% weight increase. So that was pretty good, but it falls short from what is known of the best materials. What are the materials that we're comparing with? And one is the MOF, the Metal Organic Framework, CALF 20, which is actually on the top line, which is about 4. Okay, so we were underneath of what was the state of the art. in those types of materials, or it has another mechanism. But let's just say what is out there being scaled up, and but we also look at 10% in a nitrogen carrier gas, and again, we'd expect it's slightly lower, and that's exactly what it is. But what is really cool is that if we start looking over a shorter time, 15 minutes, then our materials are competitive. The one on the left is 100%, but if we take flue gas conditions, 90 degrees, then our materials are even better than the Calf 20. And I think this is really exciting, yeah, for us. Yeah. Anyways, I have to go through a bit faster. This is just to show that the absorption cycles, we have pretty good stability of the materials. They decay a little bit over time, which is basically due to oxidation, typical for amines. And we can see that in the stress test results. Some of the different types of gases in there, if you look at the left-hand side, they're stable over, but not stable to oxidation over a longer time. And I won't talk about the permeability, but we have an idea that the reason these materials are working really great is because the permeability is increased at higher temperature. And that's all I'm going to say. Finally, this is the last slide. I will stop. And these are different types of projects. These are not the only polymers we're looking at. This is a sort of a niche area in the polymers, but there are huge waste streams in PVC, polyethylene, and so on. And we're looking at different chemical processes. I said that was the last slide. There's one more polystyrene. Ruth is out there, and she's going to be defending soon her thesis. Sorry, Ruth, for that. And then I'll just acknowledge all the team that was working with it. And thank you very much. Yeah.